Hi, we're going to move from the first law of thermodynamics to the second. And the second law of thermodynamics is sometimes referred to as the arrow of time. So it will be the law that will help us understand why reactions go in certain directions, and then also what happens when we reach equilibrium. So, 1 second. So the second law of thermodynamics. And so we have to introduce the concept of entropy and then figure out how to quantitate entropy changes. We need to think something about absolute entropy, which is the third law of thermodynamics. And then we have to understand the Gibbs function, which is a function that chemists have defined that takes advantage of entropy and the fact that it's always increasing, but puts it into terms that's easier to deal with chemical reactions. So we'll get to all of those things. So the second law is the basis of all change in chemistry, and to understand why physical and chemical changes occur, it's essential to understand the law is formulated in terms of entropy. And the second law states that the entropy of an isolated system tends to increase. It's actually a probability thing, which we won't go into too much, but if you take 366, you'll learn a lot about that concept. So a spontaneous change is a change that has a tendency to occur without you doing any work. In other words, a spontaneous change happens by itself. So there are lots of chemical reactions that you've carried out to this point in your career, and you look at them and they take place all by themselves, and so they're spontaneous. A non-spontaneous change is one that you'd have to put work into, and a good example of that is when a battery runs out, it's dead, and if you want to recharge it, you put electrical work back in, and that forces that chemical reaction that's no longer spontaneous to go in the opposite direction, and you can force it to happen. Another way to think about a non-spontaneous change is to think that the reverse of how you've written it would be spontaneous. So if it's non-spontaneous in one way, it should be spontaneous in the other direction. It's important also to think that a tendency to change, or spontaneity as a defined term, has nothing to do with how fast this is going to happen. So there are lots and lots of reactions, such as you can mix hydrogen and oxygen gas together, and that reaction is so slow, it's extremely spontaneous, can give you a lot of energy if you can get the work, or if you can get the reaction going. But the activation barrier is so high that it's just super slow, and it essentially won't happen on its own. Versus there are lots of other reactions, like I always do the demo of silver nitrate and sodium chloride. You mix them together, you get a white precipitate just instantly the second the two solutions hit each other. So it's a spontaneous process, and it's a fast process. So you want to think that reactions don't go in one direction because they're lowering their energy. Sometimes that's a thought you get after you learn about delta G, because delta G has delta H in it. And somehow you think if the process is exothermic, gives off heat, lowers its own energy, it's going to be spontaneous. But there are a couple of reasons that that makes no sense. Number one, we have an isothermal expansion of a perfect gas. So you take a perfect gas, put it in a small container, you open a valve that's empty to a bigger container, and the gas will expand. During that expansion, the energy doesn't change at all. Just a second. Hello? I've got to get that phone out of here. The energy doesn't change at all, because for a perfect gas, the volume of the container doesn't matter because the particles aren't interacting. All that matters is the temperature. So that process is spontaneous, even though the energy doesn't change. And the other one is, if you put a hot block of metal next to a cold block of metal, the heat will flow from the hot to cold. And yes, the energy of the hot metal will go down, but the energy of the cold metal goes up. So depending on how you define your system, one's gaining energy and one's losing energy. So that can't be why reactions take place, that the energy is lowered in the system. So the apparent driving force is that the energy and the matter disperse in a spontaneous process. So this top picture shows you that ideal gas, or maybe in this case even a solid, and it sublimes and fills the whole container. And in that process, it's going to be spontaneous because the matter is dispersed. Down here, it's really hard to see the little arrows, but it's showing you that the hot metal has more kinetic energy than the cold. And spontaneous change is going to be for that energy to flow from the hot to the cold. So we have the second law, which says the entropy of an isolated system tends to increase. So that means we have to be able to say all the entropy changes in the universe as a result of our reaction. So if we have a reaction in a beaker and its entropy changes, we also have to measure how the entropy changed around it in order to use the second law. You can show that a good definition of entropy is related to Q and T. And so if the process is carried out at constant temperature, change in entropy would be Q reversible over T. The reversible is important and the T is important. More general form of that definition of entropy is that ds, an infinitesimal change, is equal to dq reversible over t, and you might have to integrate over that t if the temperature isn't constant, so you may use that at some point. You can show, which isn't that hard to do, that this definition of entropy matches what we see in nature. So it matches the fact that heat flows from hot to cold. When we look at the numbers for that, it will always be true if the hot temperature is, if you're pulling some heat out of a hot place and putting it into a cold place, you'll always get a positive entropy change. Whereas if you try to do the opposite, like a refrigerator, pull heat from the inside of your refrigerator and take it outside to where it's already hotter, that's not spontaneous, and that's why your refrigerator has to be plugged in. You have to have a pump in order for that process to take place. So Atkins in this book doesn't really give you much information on where this definition comes from, but it matches physical reality, and observation is a good reason. And then it also works when we try to use it to understand the entropy changes. So why is the reversible part of that equation important? Mainly because you want it to happen slowly so that the heat is always being dispersed, versus if you did like added a bunch of heat really quickly, you might get a hot spot. And then as that disperses, you might get more entropy. And so the Q irreversible that you put in, you wouldn't necessarily see all of that being dispersed. So you wouldn't see all the entropy. Why heat and not work? Well, we know that work doesn't disperse energy. Work would be something like lifting an object against gravity. It doesn't have any more dispersal of energy up here than it had down here. Versus if I heated up that object by random motion hitting the surface, its temperature would go up and the energy would be dispersed. So entropy is related to heat and doesn't change if you just do work. And then why is the temperature in the denominator? And it's mostly this idea that if something's already hot and you add a little bit of heat to it, you're not going to change the entropy as much as a system where it's really cold and you add some heat to it. You're going to have a bigger impact. And I've always seen this analogy. It's like sneezing in a busy street where it won't even be noticed, versus sneezing in a quiet library where you'll be embarrassed probably. So it's really the difference in how much noise is already there, or in the entropy case, the difference in how much energy is already there. Entropy is a state function, and we'll see that as we go through our calculation. So it only depends on the present state. And the only other thing we're going to do in this first section is talk about heat engines. Heat engines are often used to prove things like entropy is a state function, and we're not going to do that this block, but once again, you'll go into a lot more depth if you take a higher level thermodynamics course. So we want to think about a heat engine, something like your car There are lots of examples of a heat engine. Your car uses as the hot source this red thing here, the burning of your gasoline, and then that heat flows out. Some of it does work because the heat drives an engine, so it drives your pistons. And you can't have a system where you take heat out of a hot source, so the red arrow, and all of it does work, because in all of the universe, all that would happen is you decrease the entropy of the hot source because you pulled some heat out. So Q would be negative, but you never put any heat anywhere else. So you'd have a negative entropy change. So it's impossible to have a heat engine like your car that takes all of the energy in the fuel and takes it to use to move your car. You always have to have that radiator. You always have to be cooling your engine because there's a lot of wasted heat, which is part of thermodynamics. It's not poor design. So the maximum efficiency of any heat engine, so you have to throw some heat away, and the very best you can do is 1 minus T cold over T hot, which says if you can throw the heat away to a really cold place, like absolute zero, you could have 100% efficiency, you'd have 1. Or if you can get your engine super, super hot, burn the fuel at a really high temperature, that will make this a smaller number and your efficiency gets closer to 1. But the important thing is efficiency for the thermodynamic limit is only dependent on the two temperatures, your cold source temperature and your hot source temperature. So let's just look at where that equation comes from. So in a real engine, real heat engine, you have a source of heat, probably burning a fuel. You take that heat out and run it in your engine. So move your pistons up and down with the expansion of that gas. Some of it can do work, and some of it has to be thrown away to a cold sink. You have to have a tailpipe exhausting some of that heat and your radiator. So the efficiency would be the work that you get out divided by the heat that you absorbed, so this Q hot. And if we want to figure out where this thermodynamic limit comes from, it comes from the second law. So the second law says that the total entropy change of the universe has to be positive. And if we look, when we pull heat out of the hot source, we're decreasing the entropy of the hot source. So put absolute values on this so we're not thinking about direction of the heat flow. But the heat source entropy will go down by QH over TH, whatever the temperature of that hot source is. And then when you throw it to the cold sink, you're increasing that entropy because you're adding heat. And so the absolute value of how much you put into the cold sink over the temperature cold. And this has to be positive for it to be spontaneous. And the point at which it just turns to be spontaneous is, we'll say, at 0. So it switches from negative to positive. So if the delta S total is 0, then this is negative, that's positive. So I can take the negative QH over to the left-hand side. And then it's easy to see, I can just take the T cold up here and the QH down here. And the ratio of Q cold to Q hot is equal to T cold over T hot. So if we go back to our definition of efficiency then, efficiency is the work, and the work is the difference in Q hot and Q cold. So all of these have to add up. So Q hot has to be equal to how much work you did and how much Q cold you sent away. And that's just the first law of thermodynamics. You have to conserve that energy. So work is equal to Q hot minus Q cold. And then the heat I put in is Q hot. And so this you can rearrange to be 1 minus Q cold over Q hot. And then when I look at what I just derived for that to be valid with the second law, Q cold over Q hot has to equal TC over TH. So you can just replace that ratio with the temperature ratio. And that's the thermodynamic limit. That's the very best engine you can make. And you're never going to make an engine that good. But you'll never make an engine better than that. So to change the thermodynamic limit, you can change the temperatures of your engine. To change the real efficiency of your car, you can do all sorts of things like decrease friction and change the materials that you're using. So on a functional level, you'll never get this. But to change this and to have it potentially better, you want to change the temperatures of your engine and of where you're throwing the heat away too. So heat doesn't flow from cold to hot spontaneously. You have to put work in. And the real reason you have to put work in is because if QC to the hot is all that goes in, if these two values are equal to each other, then this can never be a positive value, because the same numerator divided by a smaller denominator will always be the bigger number. So it will always be negative. So the only way to change that is to make this value bigger. And you make that value bigger by using the work of your pump in your refrigerator, which is compressing the fluid and essentially forcing that heat out. But if you add this work and dissipate it away as heat, then QC plus the work you put in can balance out the fact that this term is always going to be smaller. So that's how you will make your entropy positive for a process that wouldn't be spontaneous unless you put the work in. So there's an equation. Right here for the efficiency of a refrigerator. And then a heat pump is essentially a refrigerator too, except the goal is different. You're pumping heat from a cold place to a hot place. They're often used in climates where the winters don't get so cold because the efficiency depends on the difference in the temperature outside and inside. And so if it's too cold outside, the efficiency gets too low. So that ratio can't be too big. Otherwise, your efficiency will go way down. But a heat pump is really a refrigerator, except the goal is you're not wanting to make the outside colder. You're wanting to pump heat from the cold outside and put it into your house. So a lot of people in the Southeast will use a heat pump, and then they'll switch the circuitry in the summer and make it into an AC conditioner, so air conditioner, because it's really the same piece of equipment. Your goal is just different where the heat's going. So that is all just for an introduction to entropy. So next we'll talk about how we can calculate entropy changes during reactions and physical processes.